Tonight, our focus drifts across the vastness of space to the majestic, distant worlds that dominate the outer solar system. We're talking about the gas giants, those colossal spheres of swirling clouds and deep mysteries far beyond the rocky inner planets. These are places of immense scale and incredible phenomena, far removed from anything we experience here on Earth. We'll delve into what makes them so unique, the secrets they hold, and the incredible missions that have brought us closer to understanding them. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. Our journey begins with Saturn, a planet instantly recognizable by its spectacular ring system. For a long time, much of what we knew about this ringed jewel was based on distant observations, leaving countless questions unanswered. But then came the Cassini-Huygens mission, a truly remarkable endeavor that reshaped our entire understanding of this gas giant. It's truly difficult to fully express the profound impact this mission had. While other robotic probes had visited Saturn before, none have been as extensively groundbreaking as Cassini-Huygens. Its contributions weren't just theoretical, they were literally impactful, both in the physical data it gathered and the scientific revelations it provided. The amount of information this mission generated is staggering. Its collected data became the very foundation for over 4,000 scientific research papers, each one peeling back another layer of Saturn's intricate story. It wasn't just about observing from afar. Cassini also discovered 6 previously unknown moons, shedding new light on the planet's complex satellite system and helping us better understand their individual compositions. The sheer endurance of the mission itself is a testament to human ingenuity and engineering. Cassini survived a 20-year voyage, covering an astonishing 7 billion kilometers through the cold, unforgiving vacuum of space. 13 of those years were spent diligently orbiting Saturn, tirelessly collecting an unprecedented trove of data. This included precise measurements of Saturn's gravity, its powerful magnetosphere, the intricate structure of its iconic rings, and the composition of its enigmatic atmosphere. Even in its final moments, Cassini continued its scientific work. It gathered data right up until the very end, as it made its deliberate plunge into the swirling, mustard-colored clouds of Saturn's upper atmosphere. The spacecraft ultimately broke apart into countless pieces, a fiery end to a 2-decade-long journey. But it wasn't just about the numbers and the scientific papers. Cassini also sent back some of the most jaw-dropping, inspiring images of Saturn, and indeed the entire solar system ever captured. When you combine its immense scientific output with these stunning visuals, it becomes clear that this was an utterly extraordinary mission in every sense of the word. To truly appreciate the breathtaking splendor of Saturn, there's really no better way than to view it through the eyes of Cassini, especially during its final phase, known as the Grand Finale. Before Cassini, other probes had paved the way. The first probe to successfully reach Saturn was Pioneer 11 back in 1979. It was during this pioneering flyby that scientists made a crucial confirmation: Titan, Saturn's largest moon, possessed its own substantial atmosphere. This discovery immediately sparked a desire to return, but this time with a dedicated lander to explore what lay beneath Titan's hazy shroud. At that point, Voyager 1 and Voyager 2 were already well on their way to Saturn, making it impossible to add a lander to their missions. This necessity gave birth to the Cassini-Huygens mission. The Cassini spacecraft, with its Huygens lander nestled securely, began its epic journey on October 15, 1997, launching into the cold expanse of space. Getting a spacecraft all the way to Saturn is no easy task. The entire trip involved a constant battle against the immense gravitational pull of our own sun, which tirelessly tried to tug Cassini back into the inner solar system. To achieve the incredible speeds necessary to reach Saturn, Cassini employed a clever technique called gravitational assists, using planets as cosmic slingshots. It first flew past Venus not once, but twice, gaining momentum from each encounter. Then, it swung back towards Earth, using our home planet's gravity to slingshot it with even greater force towards the outer solar system. Finally, a close encounter with Jupiter provided the last, powerful push needed to send it hurtling towards Saturn. This precise alignment of planets, which allowed for these perfectly timed gravity assists, is incredibly rare, occurring only once every 600 years. So, the timing for Cassini's launch was absolutely critical, a narrow window of opportunity that had to be seized. Cassini's second pass by Earth was incredibly close, a truly hair-raising moment. It scraped past our planet at a mere 100 kilometers above the surface at its closest point. This already interesting fact becomes even more compelling when you consider how Cassini was actually powered. The spacecraft relied on 3 radioisotope thermoelectric generators or RTGs. Essentially, its power source came from approximately 3 kilograms of highly radioactive plutonium. The slow, steady decay of this radioactive material generated the electrical power that kept Cassini's systems running. Even at the very end of its mission, as it prepared for its final dive, it was still producing around 700 watts of power. Now, carrying such a substantial amount of radioactive material on a spacecraft does present a certain level of risk. If, for some reason, the scientists' calculations had been incorrect and Cassini had crashed back down to Earth, there was a theoretical possibility that people on the planet could have been exposed to radiation. NASA, ever thorough, estimated that in a worst-case scenario, this could have potentially caused about 5,000 deaths from cancer. However, this was deemed an acceptable risk, given that the chances of such a catastrophic event happening were astronomically low, estimated at only 1 in a million. Cassini used RTGs because, at the time of its design and launch, solar panel technology simply wasn't advanced enough to reliably power a spacecraft so incredibly distant from the Sun, where sunlight is incredibly faint. The RTGs provided Cassini with a very long operational life, and theoretically, it might still be functioning even now if it hadn't eventually run out of its crucial propellant, the fuel that allowed it to maneuver and adjust its orbit. Cassini had a multitude of ambitious objectives. It aimed to deeply understand the intricate structure and dynamic behavior of Saturn's rings, to explore its many moons more thoroughly than ever before, to measure the planet's vast magnetosphere, and to extensively study Saturn's atmosphere itself. A significant portion of its mission, however, was dedicated to Titan, Saturn's largest moon. This is where the Huygens, part of the Cassini-Huygens mission name, comes into play. Huygens was a specialized lander, designed to be released from the main Cassini spacecraft. Its sole purpose was to descend through Titan's thick, hazy atmosphere and investigate what lay hidden beneath those obscuring clouds. Huygens was actually the part of the mission built and operated by ESA, the European Space Agency. The Huygens probe itself was relatively small, about 1.3 meters wide and weighing 300 kilograms. Once it detached from the main Cassini orbiter, it embarked on a 22-day solo journey through space, slowly drifting towards Titan. During this period, the only active system on board was a precisely programmed wake-up timer set to activate the probe just 15 minutes before it was due to enter Titan's atmosphere. And when it woke up, what it encountered was truly astonishing. The core mission of Huygens revolved around its 2.5-hour descent through Titan's atmosphere, meticulously taking readings of everything from atmospheric pressure and composition to wind speeds and temperatures. Because its primary objective was focused entirely on these atmospheric measurements, its battery life wasn't designed to last much longer beyond its anticipated landing. Scientists at the time thought there was a possibility it might land in an ocean or lake, and they had designed Huygens with that contingency in mind. However, as the data later revealed, it actually touched down on what appeared to be the bed of a dried-up lake, a landscape that was both familiar and alien. The Cassini mission as a whole proved to be remarkably successful. Beyond the invaluable scientific data it collected over its 13 years orbiting Saturn, it also provided some of the most breathtaking images of space ever seen. The sheer beauty of Saturn and its moons, captured through Cassini's lens, is truly unparalleled. Some incredibly dedicated individuals have even meticulously stitched together over 1 million individual photos taken by Cassini to create stunning time lapses, giving us an immersive experience of what it would have been like to actually be sitting on the spacecraft, watching Saturn unfold. These aren't computer-generated images. They are real, only enhanced and color-corrected, then sequenced to show movement, a truly amazing feat. As Cassini's fuel reserves began to dwindle, scientists faced a critical decision: how to maximize the remaining operational life of the spacecraft and gather as much data as possible. To achieve this, they sent a series of commands to Cassini, directing it to perform extremely close flybys of Saturn and some of its inner moons. This brought the probe closer to Saturn and its rings than it had ever ventured before. This final, daring phase of the mission began on November 30, 2016. Cassini repeatedly climbed high above Saturn's North Pole, then plunged dramatically to a point just outside the narrow F ring, which marks the outermost edge of the main ring system. It completed 20 such orbits, a dance of precision and peril. Then, on April 22, 2017, Cassini executed a final, audacious leap, soaring over the rings to begin its last series of incredibly daring dives. These plunges took it directly into the uncharted territory between the planet itself and the inner edge of its rings. This was the Cassini Grand Finale, a breathtaking sequence of loops and dives that brought the probe progressively closer to its primary object of study, facing ever-increasing danger with each pass. The closer it got, the purer and richer the data became. Ultimately, Cassini would fly directly into the embrace of Saturn itself, sealing its fate and ensuring its complete annihilation. NASA's website explicitly stated the profound rationale behind this final, self-sacrificial mission. As Cassini plunged through Saturn's atmosphere during the grand finale, it was set to collect an incredibly rich and valuable treasure trove of information. Details that the mission's original planners could scarcely have imagined. The spacecraft was tasked with creating highly detailed maps of Saturn's gravity and magnetic fields. These maps would provide unprecedented insights into how the planet is structured internally, potentially helping to unravel the long-standing mystery of how fast its deep interior is actually rotating. This final phase would also vastly improve our understanding of the precise amount of material contained within the rings, bringing scientists closer to comprehending their enigmatic origins. Cassini's particle detectors were designed to directly sample icy ring particles as they were funneled into the atmosphere by Saturn's powerful magnetic field. Its high-resolution cameras captured amazing, ultra-close images of Saturn's rings and its swirling clouds, views that no other mission had ever achieved. This unique region, so close to the planet, had remained largely unexplored. The knowledge gleaned from these activities would significantly enhance our understanding of how giant planets, and indeed entire families of planets, form and evolve across the cosmos. The very end of Cassini's final orbit, as it made its inevitable fall into Saturn's atmosphere, was also a deliberate act of planetary protection. It completed its 20-year mission by ensuring that the potentially biologically interesting worlds of Enceladus and Titan would never be contaminated by any hardy microbes that might have stowed away on the spacecraft and survived the long journey intact. A tool code print Googled search. Search queries Cassini Grand Finale Scientific Objectives, Cassini Mission End Details, Saturn's Moon Atlas Features, Saturn's Moon Pan Features, Saturn's Moon Daphnis Features, Janus 2E1 Spiral Density Wave Saturn's Rings, Saturn's B-ring density waves explained, Janus Epimetheus Orbital Swap Period, Cassini Propeller Features Saturn's Rings, Saturn's F-ring Solid Objects, Saturn's northern hexagon changes over time, Saturn's polar vortex hurricane, Saturn's atmospheric haze stratosphere, Cassini Enceladus Plumes E-ring connection, Enceladus water plumes discovery Cassini, Saturn's E-ring characteristics, Saturn's night side illumination by rings, Saturn's terminator line cloud shadows Cassini, Cassini Dione ripples, Cassini Titan final images, Cassini final plunge details atmosphere, Cassini final data collected, Cassini post, mission discoveries Saturn's mysteries, Saturn's magnetic field alignment mystery, Saturn's day length measurement challenges, Saturn's aurora origin non-solar, Saturn's internal heat source mystery, Saturn's liquid metallic hydrogen diamond rain, Saturn's conductive layer magnetic field explanation, Saturn's day length from ring gravity ripples, NASA Dragonfly mission Titan focus, Titan's atmosphere and surface features, Saturn's ring age and dissipation theories. This ending, full of inspiration, adventure, and even a touch of romance, provided a truly fitting conclusion to an exciting story of exploration. But let's take a much closer look at some of those last, dramatic moments during Cassini's grand finale. NASA made a conscious decision to prioritize an unprecedented level of closeness to Saturn over Cassini's potential for a longer operational life. This was an easy choice, though, because Cassini was already on its last drops of fuel, so its continued survival was simply not an option. Making this decision allowed Cassini to approach the planet more intimately than any spacecraft had before, weaving daringly between the magnificent rings. So, what did it actually see during these final, perilous passes? Did this unique, up-close perspective reveal anything entirely new, things we'd never witnessed before? Let's dive into some of the incredible sights Cassini captured during its grand finale. Starting with Saturn's moons, Cassini managed to observe some of the smaller, shepherd moons, with truly incredible detail. One such example is Atlas, a small moon, only about 40 kilometers across, orbiting near the outer edges of the A-ring. What's truly striking about Atlas is its surprisingly smooth surface, with a remarkable lack of impact craters, giving it an almost bizarre, otherworldly appearance. Scientists believe that dust from the surrounding rings has gradually accumulated on its surface, particularly around its equator, effectively smoothing it over and giving it this distinctive, disc-like shape. A similar phenomenon occurs with Pan, Saturn's second innermost moon. Pan is a bit smaller, 30 kilometers wide, and resides within the Encke Gap, a 350-kilometer wide division in Saturn's A-ring. Any particles from the rings that stray into this gap are efficiently swept up by Pan. This constant sweeping action is what helps maintain the Encke Gap, keeping it clear and stable. Another shepherd moon, Daphnis, though not observed in quite as much detail, also plays a crucial role. Its effects are visible for hundreds of kilometers around it, due to the gap it inhabits. Daphnis is tiny, only 8 kilometers in diameter, and is found within a very narrow opening in the A-ring called the Keeler Gap. Its gravitational pull is incredibly weak, but it's just strong enough to gently perturb the nearby dust particles as it glides past. This creates fascinating waves or ripple effects in the surrounding ring material, sometimes even tearing material directly out of the ring, leaving a faint trail behind it. These ripples aren't just moving side to side, they also extend upwards and downwards, which is clearly visible from the shadows they cast on the rings. One can only imagine the surreal experience of sitting on Daphnis, watching these graceful waves follow its orbital path, with the glorious ringed giant Saturn and its many moons stretching out in the background. It would be an absolutely breathtaking sight to behold. Speaking of the rings, Cassini captured some truly spectacular images during its final phase. One of the most fascinating from the grand finale showcases what's known as the Janus 2-in-1 spiral density wave. What you're actually looking at here is the result of the same fundamental process that creates spiral galaxies, only on a much smaller scale and incredibly more tightly wound. What appears to be numerous separate rings in the image are, in fact, only two distinct spiral arms wrapping around the planet many times. This means that every second line you see in the image belongs to the same spiral arm. This particular image is part of Saturn's B ring, located at a position where the ring material orbits twice for every single orbit of Saturn's moon, Janus. This creates a powerful orbital resonance. The photo itself gives a subtle illusion that the image is tilted away at the upper left, but this isn't actually the case. The optical trick is created by the specific way these density waves propagate outwards from the planet, with their wavelength decreasing as they get further from the point of resonance. And this is where the resonance phenomenon becomes even more mind-blowing. Janus, the moon responsible for contributing to this particular resonance, actually switches orbital positions every 4 years with its close neighbor, the moon Epimetheus. Each time this orbital swap occurs, the rings respond, generating a new crest in these waves. NASA scientists explain that the distance between any pair of these crests corresponds to 4 years of the wave propagating downstream from the resonance point. This means that the wave patterns visible in this image actually encode many decades worth of the orbital history of Janus and Epimetheus. According to this interpretation, the part of the wave at the very upper left of this image corresponds to the positions of Janus and Epimetheus around the time of the Voyager flybys in 1980 and 1981. This was the exact period when Janus and Epimetheus were first definitively proven to be two distinct celestial objects. This kind of historical encoding within the rings reminds one a little of a tree trunk, with its growth rings recording the tree's age. It's truly amazing. Beyond these beautiful and incredibly detailed images of the rings, Cassini also observed other interesting features, particularly tiny propeller features, scattered across various locations within the rings. One image might show both sides of the rings, the top portion revealing the illuminated side and the bottom showing the unlit side. Scientists use this comparative view to analyze and try to decipher subtle details. Even though the scale of the image is immense, with each pixel representing about 500 meters, the tiny moonlet causing the propeller might not even be directly resolvable. You might just catch a faint trace of it in the top image. But what is clearly visible is that this moonlet is physically connected to the surrounding ring material by a distinct band of particles. As mentioned, this wasn't the only tiny moonlet attempting to carve out a gap in the rings. Cassini found another right next to the Encke gap, and yet another, probably the largest of these three. None of these moonlets are believed to be larger than 2 kilometers across and likely have a density similar to that of a snowball. The last intriguing thing Cassini managed to image within the rings were extremely small, but apparently solid, objects that had formed around the E-ring. These formations are potentially caused by the gravitational perturbations of some of the shepherd moons in that region. They appear to be solid because they have survived repeated collisions with the E-ring, kicking out dust and particles. Sometimes, these ejected particles even follow the object's orbit, creating a visible haze around them. The objects themselves aren't actually visible due to the obscuring dust. Finally, let's turn our attention to the planet Saturn itself. At the time Cassini flew by, Saturn's northern hemisphere was experiencing full summer. This meant its remarkable, six-sided hexagon storm encircling the North Pole was in perfect view. At the very center of this hexagon lies a permanent polar vortex, essentially the eyewall of a truly massive hurricane, dwarfing anything seen on Earth. Interestingly, this polar region seems to be changing color with the seasons. A comparison to 2012 shows a much darker pole, highlighting a clear seasonal shift. With the assistance of other wavelengths of light, various other storms become visible, scattered across the planet, as well as distinct bands reminiscent of Jupiter's, but not quite as vivid in natural light. Also, due to Cassini's close proximity to the planet, it was able to capture an excellent view of Saturn's horizon. On the left side of one particular image, a faint haze can be seen in the stratosphere of the atmosphere, gradually disappearing towards the right side of the image. When Cassini finally began its terminal dive into the atmosphere, it was initially thought that it wouldn't even survive long enough to reach this stratospheric haze. However, scientists weren't overly concerned about that specific detail. What truly fascinated them was the exact composition of Saturn's atmosphere. Cassini was designed to plunge into that atmosphere, collecting this vital information right up until its destruction, making these the very last readings the spacecraft would ever transmit. Yet, even 1 week before its final atmospheric entry, Cassini was still diligently capturing images. Some of these last photographs are truly fantastic. It's important to remember, though, that Cassini wasn't capable of real-time video capture. The videos we might see are actually time lapses, meticulously spliced together from countless individual images, creating glorious visualizations of what it would have been like to fly with Cassini on its ultimate journey into Saturn. Not all of these final images were of Saturn itself. The first time lapse we'll consider was taken on September 8, 2017, just 1 week before the mission's end. One of Cassini's major areas of focus throughout its mission was the Moon Enceladus, considered one of the prime candidates in our solar system for potentially harboring life in a subsurface ocean. Cassini famously discovered over 100 powerful water plumes erupting through the Moon's icy crust, spewing water from this hidden ocean into space. This water then freezes in the frigid space environment and has, over time, formed the beautiful E ring around Saturn. This particular ring is incredibly tenuous, only visible when backlit by the sun, and it's potentially the bluest naturally occurring object in the entire solar system. There's a fantastic view showing Enceladus's direct effect on the densest part of the E-ring, where you can clearly see the plumes actively disturbing and replenishing the ring material. Cassini's final look at Enceladus's plumes was captured in a truly remarkable time lapse, spanning a 14-hour period. On September 11th, Cassini was near the furthest point of its final orbit and captured a breathtaking mosaic image in natural light. Visible are the thickest of Saturn's rings, D, C, B, A, and F, with Saturn's relatively short shadow gracefully cast over them. Saturn's northern hemisphere was still basking in summer during this time, meaning its most famous hexagonal storm was visible in all its glory. You can also just about make out Saturn's subtle atmospheric bands in natural light. What's truly fascinating about this image, however, is that the night side of Saturn is dimly illuminated. This is due to the immense amount of light reflecting off the rings, meaning Saturn's nights, at least in the hemisphere facing the sun and rings, never get completely dark. Below the glow of the rings, however, Saturn remains truly pitch black. As Cassini began to approach Saturn once more on September 12th, it captured images of Saturn's atmosphere near the planet's terminator line, the boundary between day and night. Incredibly, because the sun is so low in the sky in this region, enormous cloud structures can be seen casting shadows that stretch for many kilometers across the planet. You might initially think this is a close-up of Saturn, but in reality, we're looking at a scene spanning approximately 5,500 kilometers across, an area large enough to easily fit Saturn's moon Titan within the frame. Cassini was getting closer and closer to its ultimate destination. On September 13th, it took one last look at Daphnis, and keen observers will notice ripples not only in front of the moon, but also behind it. This phenomenon is explained by the differing orbital speeds of the rings and the moon. The inner ring material orbits faster than Daphnis, meaning the ripples effectively overtake the moon, exposing more ring material to its gravitational pull. Conversely, the outer ring material travels slower than Daphnis, so the ripples lag behind the moon. By the time the ring material circles back to Daphnis on either side, these ripples have already smoothed out. On that very same day, Cassini took one final glance around the broader Saturnian system. It captured a view of Titan, a moon it had studied extensively throughout its mission, a truly remarkable world with a thick nitrogen atmosphere. It also observed Saturn's rings, with the uneven F-ring just barely visible at the bottom of the image. As Saturn grew larger in its field of view, Cassini took one last, 40-minute look at Enceladus before the icy moon finally disappeared from view behind the limb of Saturn. The very final image Cassini ever captured was looking over the specific region where it was destined to plunge into the atmosphere. It was nighttime here, and so Saturn was lit up by the ethereal light reflected off its rings. On the mission's absolute final day, capturing more beautiful photos wasn't on the scientists' agenda. As stunning as they are, images consume a lot of valuable bandwidth, and scientists desperately wanted to receive every single bit of real-time data before the spacecraft was ultimately destroyed. This was an absolutely unique and unparalleled opportunity. Humanity had never before directly probed Saturn's atmosphere. When Cassini first encountered the tenuous outer layers of Saturn's atmosphere, it was traveling at an astounding 123,000 kilometers per hour. The last remnants of Cassini's precious fuel were deployed by its thrusters, desperately trying to keep the spacecraft's antenna precisely aimed at Earth, ensuring the continuous transmission of data. At this point, Cassini was approximately 1,900 kilometers above Saturn's main cloud tops. Just a minute later, these thrusters were firing at their absolute maximum capacity, struggling to prevent Cassini from spinning wildly out of control. Cassini was now directly sampling Saturn's atmosphere, but this atmosphere was also generating immense heat, rapidly raising the spacecraft's temperature. A mere 10 seconds after that, the thrusters were simply overcome. Cassini began to tumble uncontrollably, severing its communication link with Earth. At this critical moment, Cassini's onboard computers would have been frantically trying to diagnose what was going wrong. Its gyroscopes and star trackers would have reported the uncontrolled spinning, and the system would likely have entered a safe mode to divert power in a desperate attempt to correct its orientation. A minute or so later, the spacecraft would have disintegrated entirely, burning up completely in Saturn's dense atmosphere. When the final data started arriving on Earth, approximately an hour and a half later, this last, perilous part of the mission was deemed a resounding success. Cassini had recorded invaluable data from direct analysis of Saturn's atmosphere, its ionosphere, dust particles suspended in the atmosphere, and from magnetic field measurements. And perhaps even more secrets are yet to be uncovered as scientists continue to pore over the vast amounts of information. That's the truly amazing thing about the Cassini mission. It just keeps on giving. Scientific papers and new discoveries are still being made, even years after its end, as the immense dataset it collected is meticulously analyzed and re-examined. So, what exactly have we learned from Cassini's data in the years since its groundbreaking mission concluded? You're about to find out. But be prepared. Some of the things Cassini revealed about Saturn have only served to make the planet even stranger, deepening its enigmas. You might think you know Saturn. Its iconic rings are undeniably the largest and most spectacular in our solar system, and its hazy, yellowish surface is both mysterious and instantly recognizable. It is the second largest planet, the least dense of all planets, and the sixth planet from the Sun. And yet, Saturn remains a profound enigma. There's a vast, hidden mystery lurking beneath its obscuring atmosphere, a secret uncovered by the Cassini probe, one that the scientific community still does not have a definitive consensus about. Saturn seems to behave in ways that our conventional planetary models claim are simply impossible, from its internal temperature to the nature of its magnetosphere, and even to the very precise length of its days. What exactly is going on with Saturn, and what are our best attempts at explaining these baffling phenomena? The Cassini probe first arrived at the gas giant on July 1, 2004. It wasn't the first spacecraft to reach Saturn. 3 others had already performed flybys. However, as we've already discussed, Cassini was by far the most thorough, spending 13 dedicated years circling the planet, collecting immense quantities of data using its various spectrometers, magnetometers, and other sophisticated equipment. The knowledge it imparted has been of immense benefit, but sometimes it only served to deepen Saturn's mysteries. Consider, for example, that enormous hexagon storm at Saturn's North Pole. The sheer scale of this storm is mind-boggling. Its edges span 29,000 kilometers, an area large enough to comfortably fit the entire Earth inside each side. And as far as we can tell, it doesn't shift its longitude, remaining fixed at its location and rotating along with the planet, unlike the rest of Saturn's swirling clouds, which are pushed along by its powerful winds, reaching speeds of up to 1,800 kilometers per hour. This storm is undeniably strange. Scientists don't yet have a complete explanation for its existence or its hexagonal shape, although some lab experiments have managed to create close approximations of hexagons on much smaller scales. But the hexagon isn't an isolated anomaly. As the vast mountains of Cassini data began to be analyzed in the years since the mission's end, even more mysteries started to emerge. It all began with a seemingly innocuous question: how long is a day on Saturn? Although humanity has observed Saturn in our night sky for thousands of years, scientists still didn't have a definitive answer. After all, it wasn't as simple as looking up at the planet and timing how long it took for its solid, rocky core to rotate. Saturn's thick, opaque cloud cover completely obscures any potential landmarks that might exist on a hard surface below. And those clouds themselves move at different speeds than the planet's core, driven by incredibly powerful winds. Even the rings themselves orbit Saturn at varying speeds, so they couldn't settle this question either. You can't just look at how fast the rings orbit and assume it's the same as the planet's rotation, as most moons don't do this, and rings are no different. Rather cleverly, scientists do have established techniques for determining the rotation rate of a gas giant, primarily by examining its magnetic field. It was initially hoped that this method could be successfully applied to Saturn. Planets with magnetic fields generate them through a process known as a dynamo effect. As the planet rotates, vast quantities of liquid metal within its core spin and shift. This colossal motion of charged molecules creates massive electrical currents, which in turn produce powerful magnetic fields. A key characteristic of this dynamo effect is that, due to the planet's rotation, the pole of this magnetic field is always slightly offset from the planet's actual axis of rotation. If the two were perfectly aligned, the magnetic field wouldn't be stable and wouldn't survive for long. So, theoretically, all you need to do is detect the magnetic fields around a planet, which Cassini was perfectly capable of doing, and then observe as the magnetic pole subtly shifts in a circle around the planet's true axis. Once the magnetic pole completes one full rotation, you have accurately determined the length of its day. However, Saturn, it turns out, doesn't seem to play by these established rules. Its magnetic pole is almost perfectly aligned with its axis of rotation to an astonishing degree of accuracy, less than 0.1 degrees. And despite dynamo theory emphatically claiming that this should be impossible for a stable, long-lasting magnetic field, Saturn's magnetic field is undeniably alive and well. Its magnetic moment is an incredible 580 times more powerful than Earth's, and it exerts an extremely influential force on the entire Saturnian system. Scientists are at a loss to explain how this magnetic field occurs, as it contradicts current dynamo theory. Yet, no other proven method for producing such a powerful planetary magnetic field exists. It's likely that a planetary dynamo is indeed at play within Saturn's core, but some other, as yet unknown effect is occurring in the planet's atmosphere or deeper layers to warp the magnetic field lines, causing them to appear perfectly aligned with the axis of rotation. Or, perhaps, we are observing a completely new, previously unknown method of producing a planetary magnetic field on Saturn. So, it was back to the drawing board for solving the mystery of a Saturnian day. Fortunately, radiation proved to be of more assistance. Saturn is an electrically active system. Charged ions move constantly between the layers in its atmosphere, and even between its rings and its ionosphere. Scientists observed that Saturn emitted radio waves as a result of all these complex magnetic fields at play, and these radio waves rose and fell in intensity in a rhythmic pattern. In fact, it seemed to mirror exactly what you would expect to see as a result of a rotating planet. Higher levels of radiation would appear approximately every 11 hours or so. As a result, scientists initially concluded, with some degree of certainty, that this was indeed Saturn's day length. Their initial estimate, based on data from the Voyager missions, was 10 hours, 39 minutes, and 23 seconds. It was hoped that Cassini would be able to refine and improve the accuracy of this figure. Initially, Cassini seemed to do just that. But then, things got really strange. Over the course of Cassini's 13-year study of Saturn, this number, the presumed day length, began to subtly shift. It drifted by about 1% over the course of a year, sometimes rising, sometimes falling. This almost seemed to imply that the planet itself was altering the speed of its rotation, sometimes speeding up and sometimes slowing down. To be absolutely clear, a planet as massive as Saturn simply should not be doing that. Therefore, scientists concluded that this wasn't actually happening. Instead, some other effect must once again be muddying the waters around Saturn, obscuring the true picture. Some aspect of the atmosphere was causing these shifts in the magnetic fields, making the radiation fluctuate over time, effectively hiding the planet's true rotation beneath a shimmering, cloaking effect. Another major consequence of the planet's powerful magnetic field is the stunning auroras that glow at Saturn's poles. But while on Earth, our auroras are primarily the result of solar wind particles interacting with our atmosphere. It's believed that this doesn't fully account for the auroras on Saturn. Cassini detected that at least some of Saturn's auroras occurred independently of what the solar wind was doing at the time, meaning that at least a portion of Saturn's auroras are non-solar originating. Something strange and powerful must be occurring deep inside Saturn to produce these light shows. Saturn also proved to be hotter than it should have been. It radiates out into space about twice as much energy as it receives from the Sun. While some of this excess heat can be attributed to the slow, steady gravitational compression of the planet, the remaining energy required some other explanation. Ultimately, all of these puzzling observations cried out for a unifying explanation. And, fascinatingly, thanks to Cassini's extensive data, scientists discovered that the key to understanding all of it might lie within Saturn's gaseous atmosphere itself. Saturn is, after all, a gas giant. It's composed almost entirely of hydrogen and helium. However, not all of this material remains in a gaseous state. Due to Saturn's immense mass, the deeper you descend into its atmosphere, the more intense the heat and pressure become. It's thought that this extreme pressure forces gaseous hydrogen to transition into a liquid metallic state. Some scientists even theorize that this liquid hydrogen, or perhaps even hydrogen compressed so densely that it transforms into solid diamond, actually rains down into the deepest depths of Saturn. The immense friction generated by this diamond rain could explain some of Saturn's unusual internal heat. However, the remaining excess heat and the non-solar auroras are thought to come from the auroras themselves. Although these auroras aren't fully understood, it's theorized that they are the product of electrically charged particles entering Saturn's atmosphere from its rings and moons. Whatever their ultimate source, these auroras may be generating enough heat to warm the planet's upper atmosphere to surprisingly high temperatures. Such incredibly hot temperatures create further effects. Where warm fronts meet colder regions, powerful winds are formed. It's theorized that these intense winds carry charged ions around Saturn's upper atmosphere, and it's these electrically charged winds that are skewing the data from Saturn's radiation, causing its observed variance. Perhaps such vigorous motion of electrical currents might also explain why Saturn's magnetic fields are not aligned as expected. This could be caused by a highly conductive layer within Saturn's clouds moving at a different speed to the other layers, effectively creating its own localized magnetic fields. At least, that's one leading explanation. In all of this, it should be clear that many of these proposed answers still lack definitive proof. Scientists are diligently sifting through the enormous dataset provided by Cassini, hoping for further insights and conclusive evidence. If these insights aren't forthcoming, then ultimately, it will take another dedicated mission to Saturn to truly find the answers to these perplexing questions. But what about the length of Saturn's day? Thankfully, this one particular mystery does seem to have found an answer, and it turned out the crucial clue lay in the rings after all. Rather than focusing on the electrical and magnetic effects of Saturn on its rings, scientists realized that Saturn would also exert a gravitational influence on them. This is fairly obvious, but what was more insightful was that Saturn wouldn't pull at its rings uniformly. Saturn isn't a perfectly round, smooth ball. Any slight variations in its shape would result in corresponding variations in its gravitational field. Saturn's rings, with their vast expanse of orbiting particles, provided a perfect canvas to detect such subtle gravitational variations. As Saturn pulled at its rings with a force that subtly rose and fell in certain locations, it would induce detectable ripples. Scientists began actively searching for these ripples and successfully located them. By meticulously measuring the distance between these ripples, it was finally possible to calculate the precise length of Saturn's day. They weren't far off from earlier estimates. The definitive answer was 10 hours, 33 minutes, and 38 seconds. And this time, scientists are fairly certain that they've got it right. So, at least this one persistent mystery was finally solved. And yet, Saturn's other profound mysteries still persist, waiting to be unraveled. The next major mission to Saturn is scheduled to launch in 2027. This mission, NASA's Dragonfly, will primarily focus on extensively exploring Titan, Saturn's largest moon. Titan is, in many ways, the most Earth-like object in our entire solar system. It's the only other place known to have a thick atmosphere filled with nitrogen, much like ours, though it notably lacks oxygen. It also features rain cycles and liquid lakes on its surface, although these are composed of methane, not water. So, it's entirely understandable why scientists are so eager to give it such a thorough look. Still, this means it may be some time before Saturn's deepest, most baffling mysteries finally find their answers. Saturn itself seems to breathe its powerful winds, which might prove to be the lifeblood of the entire system, thrumming and flowing across its immense atmosphere. Its delicate balance of magnetic fields and gravity coaxes its rings, keeping them in their perfectly aligned, magnificent configuration. Saturn's rings are believed to be surprisingly young. While Saturn itself may be over 4 billion years old, there's compelling evidence suggesting that the rings may have only formed within the last 100 million years. And, sadly, they are slowly but steadily draining back down into Saturn's atmosphere. So, in another 100 million years, they may very well be gone entirely. This realization brings a strange sadness, but also a sense of profound fortune. If humanity hadn't arrived when we did, we might have completely missed this breathtaking cosmic spectacle. It might seem unscientific to say that a planet has no real choice in whether it bestows a gift upon us or not, but I am nonetheless deeply grateful to have been a witness to the enigmatic and wondrous world that is Saturn. And seeing those enigmas and wonders, all that beauty, and all that invaluable scientific data, simply would not have been possible if it hadn't been for the incredible Cassini-Huygens mission. This truly was one of the greatest space missions of our time. Our journey through the outer solar system now shifts to Jupiter, a colossal world of immense storms, deadly radiation, and captivating beauty. It's a true powerhouse whose sheer mass is so great that it actually influences the Sun itself. Jupiter is rapidly becoming one of the most intensely studied objects in our solar system. With 7 flybys and 2 dedicated orbiters, one of which is still actively operating today, plus 2 additional planned missions. There is an incredible amount to learn about this 5th planet from the Sun. What gives it its distinctive red coloration? What is it fundamentally made of? What lies hidden beneath its obscuring, swirling clouds? What do we truly know about its famous Great Red Spot? Jupiter plays a vital, protective role in safeguarding our entire solar system, and it's now time to delve deep into its many mysteries. Jupiter, the 5th planet from the Sun, is found just beyond the main asteroid belt, situated between the orbits of Mars and Saturn. It orbits at an average distance of 778 million kilometers from the Sun, which is about 5.2 astronomical units. It completes one full orbit around the Sun every 12 Earth years. The planet's axial tilt is quite small, only about 3 degrees. This means that unlike Earth and Mars, Jupiter doesn't experience much in the way of distinct seasons. Much like Saturn, its radius at the equator is noticeably greater than at its poles, a result of its rapid rotation. Jupiter is, quite simply, massive. It is the largest planet in our entire solar system. Its mass is truly colossal, 1,000th that of our Sun. That might not sound like a lot at first glance, but once you realize that our Sun accounts for 99.86% of all the mass in the entire solar system, you quickly understand that Jupiter alone makes up almost all of the remaining mass. In fact, its mass is 2.5 times that of all the other planets in the solar system combined. This immense mass leads to a fascinating phenomenon, the barycenter, or the common center of mass, between Jupiter and the Sun is actually located above the surface of the Sun at 1.68 solar radii from the Sun's center. Let's talk a bit about barycenters. When we typically think of one object orbiting another, we don't necessarily consider that the smaller object has a significant gravitational influence on the larger one. That's because, most of the time, the effect is negligible. Think of the International Space Station orbiting Earth, or even Mercury orbiting the Sun. But the gravitational influence is always there, no matter how small. A barycenter is essentially the center of mass between two orbiting objects, or more precisely, the specific point in space around which both objects actually orbit. Given Jupiter's immense mass and its considerable distance from the Sun, its effect is far from negligible. As Jupiter swings around the Sun, both the Sun and Jupiter perform a subtle dance around this common center of mass, which, remarkably, lies beyond the Sun's visible surface. Let me illustrate this principle with a simple example. Imagine taking a heavy object and a less heavy object and attaching them to the ends of a long stick. To balance the stick, you need to find its center of mass. As you can see, the center of mass will always be closer to the heavier object. Now, imagine the heavier object is the Sun, the lighter object is Jupiter, and the stick represents the invisible force of gravity connecting them. This analogy helps to understand how a barycenter works, especially when one object is overwhelmingly more massive than the other, but not infinitely so. While Jupiter possesses the greatest mass of any planet in our solar system, it's not actually the densest. It's the most massive simply because it's the largest in terms of volume. If, for instance, Neptune were the same size as Jupiter, it would actually be more massive because it's denser. Conversely, if Jupiter were the same size as Earth, Earth would be over 4 times more massive. As it stands, Jupiter's diameter is a staggering 11 times that of Earth, and its total mass is 318 times greater than Earth's. As we know, mass directly affects gravity. This means Jupiter exerts an enormous gravitational pull, over twice that of Earth. At its cloud tops, the gravity is approximately 25.28 meters per second squared, or 2.528 Gs. That's a significant force. Jupiter's gravity is so profoundly influential within the solar system that it affects every other planet to some degree or another. Its gravitational force is strong enough to rip asteroids apart and has captured at least 67 known moons, with more likely to be discovered. Some scientists even believe that Jupiter destroyed many celestial objects in the ancient past and also prevented other planets from forming in the region of the asteroid belt. A prime example of this is the asteroid Vesta, which shows clear signs of having been profoundly affected by Jupiter's immense gravity. Scientists even predict that Jupiter's gravitational influence is so significant throughout the solar system that it is subtly perturbing Mercury's already eccentric orbit. They theorize that in a few billion years, this tiny inner planet may either crash into the Sun or be ejected from the solar system entirely, flung out into the cold void. However, for now, Jupiter could be considered the hero of the 4 inner, rocky planets. Without Jupiter acting as a colossal cosmic vacuum cleaner, it wouldn't be sucking up dangerous objects like long-period comets or perturbing their orbits just enough to give them a kick of energy that sends them out of the solar system altogether. Jupiter is the 5th planet from the Sun, and it's 5 times further away from the Sun than Earth is. Even at that immense distance, it can be the 3rd brightest object in our night sky, surpassed only by the Moon and Venus. Just to illustrate its brightness, even a simple handheld camera can easily capture Jupiter in the night sky. With a maximum magnitude of -2.94, it's actually bright enough to cast visible shadows here on Earth. Because it's so prominent in the sky, it makes an excellent target for amateur astronomers. With recent improvements in consumer telescope technology, it's truly amazing what details you can discern from your own backyard. So, what creates those famous, colorful patterns we see on Jupiter. The cloud layer itself is only about 50 kilometers thick and is primarily composed of ammonia crystals, much like on Saturn. However, the distinctive coloration comes from compounds that heat up deep within Jupiter's interior and then rise to the surface. These compounds are known as chromophores, and when they reach the upper clouds, they interact with the sun's ultraviolet light, creating those spectacular, multicolored bands. This is quite a dynamic cycle, and the face of Jupiter can change dramatically over time. Even if their colors do shift, the actual latitude of these bands remains consistent enough for scientists to give them identifying designations. However, their width can certainly vary over time. Many storms and intense turbulence occur where these bands meet, and this turbulent interaction is the very engine behind Jupiter's most famous feature, the Great Red Spot. This storm is truly enormous. The entire diameter of Earth could easily fit within it. It has existed for as long as humanity has been able to observe it, ever since its first documented discovery in the 17th century. It might very well be a permanent feature of the planet. But interestingly, it has noticeably decreased in size since observations first began. The precise reason for its reddish color remains unknown, and the spot's color can vary greatly, from a deep brick red to an almost white hue. The most tonight, our focus drifts across the vastness of space to the majestic, distant worlds that dominate the outer solar system. We're talking about the gas giants, those colossal spheres of swirling clouds and deep mysteries, far beyond the rocky inner planets. These are places of immense scale and incredible phenomena, far removed from anything we experience here on Earth. We'll delve into what makes them so unique, the secrets they hold, and the incredible missions that have brought us closer to understanding them. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. Our journey begins with Saturn, a planet instantly recognizable by its spectacular ring system. For a long time, much of what we knew about this ringed jewel was based on distant observations, leaving countless questions unanswered. But then came the Cassini-Huygens mission, a truly remarkable endeavor that reshaped our entire understanding of this gas giant. It's truly difficult to fully express the profound impact this mission had. While other robotic probes had visited Saturn before, none have been as extensively groundbreaking as Cassini-Huygens. Its contributions weren't just theoretical, they were literally impactful, both in the physical data it gathered and the scientific revelations it provided. The amount of information this mission generated is staggering. Its collected data became the very foundation for over 4,000 scientific research papers, each one peeling back another layer of Saturn's intricate story. It wasn't just about observing from afar. Cassini also discovered 6 previously unknown moons. Recent theory for its color suggests that it's due to simple chemical compounds being broken apart by sunlight in the planet's upper atmosphere. These compounds are known as chromophores. Because the storm is actually much higher up in the atmosphere than the surrounding clouds, it can interact with the sun's ultraviolet light much more directly. This increased exposure would explain why its color can be far more intense than anything else around it. But Jupiter doesn't just have one scientifically intriguing storm. Another prominent storm, known as Red Spot Junger, formed when 3 smaller, white oval-shaped storms merged into a single, larger entity between 1998 and 2000. So far, it has managed to pass by its much larger neighbor, the Great Red Spot, without being absorbed or destroyed, and it has now become a quite prominent feature on the planet. This smaller red spot could potentially last for another couple of hundred years. If it continues to avoid the same fate as a similar storm that once passed directly through the heart of the Great Red Spot and disappeared. So, what do we think Jupiter is actually made of? Much like Saturn, beneath its thick atmosphere, hydrogen exists in various forms, first as a gas, then as a liquid, and then, under extreme conditions, as a metallic liquid. The deeper you go into the planet, the greater the pressure becomes. Under immense pressure, hydrogen behaves like a metal, conducting heat and electricity. Beneath that, models suggest there's either an ice core or a rocky core. Because we cannot recreate the immense pressures and temperatures found within Jupiter here on Earth, our understanding of the exact properties of these materials at the core remains somewhat theoretical. Roughly 90% of Jupiter's mass is thought to be hydrogen, with about 10% helium, and then trace amounts of other elements like methane, ammonia, and water. Jupiter rotates incredibly fast, faster than any other planet in our solar system, completing a full rotation in just under 10 hours. However, because it lacks a solid surface, it doesn't rotate at the same speed all over. A rotation at the poles takes about 5 minutes longer than at the equator, a phenomenon known as differential rotation caused by its powerful winds. As a child, I was very curious why Jupiter wasn't a star, considering its immense mass and its predominant composition of flammable hydrogen. Surely, I thought, someone just needed to throw a match in to set it alight. Well, the disappointing news for my inner child is that stars don't really work that way. Plus, there's barely any oxygen on Jupiter to allow for sustained combustion. Stars generate their immense heat and light from nuclear fusion, a process driven by the extreme pressures and temperatures found at their cores. Current scientific thinking suggests that Jupiter would need to be roughly 75 times more massive than it is now to have enough mass to ignite nuclear fusion and become a star. Interestingly, its volume isn't too far off from that of the smallest known red dwarf stars, but mass is the crucial factor. And yes, you may have noticed in some images that Jupiter does indeed have rings. They're nothing on the spectacular scale of Saturn's, but there are 4 distinct planetary rings. The main ring is very thin but relatively bright, while the others are quite wide but exceptionally faint. The main ring is about 6,000 kilometers wide, and one of its few distinctive features is what's known as the Metis notch. These rings are composed primarily of dust particles, likely created by impacts on Jupiter's small inner moons. Something else to note about Jupiter is its remarkably strong magnetosphere. It is 14 times more powerful than Earth's, primarily due to the planet's vast region of liquid metallic hydrogen in its interior. This makes it the strongest magnetosphere of any planet in our solar system, only surpassed by the Sun's sunspots. There are a couple of reasons why this is incredibly interesting. First, magnetospheres channel solar wind particles to the planet's poles, which then produces magnificent auroras, much like Earth's northern and southern lights. The second reason is that Jupiter's 4 biggest moons are largely protected from this solar wind because they orbit entirely within the magnetosphere. This implies they don't necessarily need their own strong magnetospheres, as Jupiter is effectively doing that job for them. However, this doesn't mean they are entirely safe from radiation. Jupiter is surrounded by an incredibly powerful radiation belt, a donut-shaped region of high-energy charged particles, including electrons, protons, and ions. This same radiation belt has crippled or damaged any probe that has ventured too close or spent too much time within it. Io, the closest large moon to Jupiter, passes directly through the heart of this intense radiation band, receiving an astonishing 3,600 rem per day on its surface. For comparison, anyone exposed to this much radiation would likely be dead within 4 hours. Not exactly the best place for a home away from home, then. When it comes to the Jovian moons, I'll only briefly touch upon them here. as I've made a separate video dedicated entirely to them. Jupiter has at least 97 known natural satellites. 51 of these are under 10 kilometers in diameter. But the largest, known as the Galilean moons, are some of the biggest moons in the entire solar system. They are Europa, Ganymede, and Callisto. All of them are fascinating worlds in their own right. Ganymede, in particular, is actually the largest moon in the solar system, with a greater diameter than that of the planet Mercury. With this final thought, take a look at Jupiter through infrared imaging, which truly demonstrates the immense size and power of this planet. That tiny dot you see at the bottom of the planet is the impact site of an object from space. If an object of that size had hit Earth, it could have spelled the end of our planet as we know it. We can be incredibly glad that Jupiter is there, not only for its captivating beauty, but also because, in so many ways, it serves as a crucial asset to our solar system, acting as a cosmic protector. Thank you so much for watching this far. Did you learn something new today about Jupiter that you never knew before? And what planet remaster would you like to see next on this channel for this series? Let me know in the comments below, and I'll see you next time. Our journey now takes us further out into the cold, silent reaches of the solar system, to Uranus, often referred to as an ice giant. This distant, bluish-gray marble might appear like a desolate, unchanging wasteland. But in reality, there are some truly fascinating aspects about this planet that make it utterly unique, unlike anything else we've encountered in our solar system. Stick with me on this exploration, and we will uncover almost everything you could possibly want to know about Uranus. The first distinctive characteristic of Uranus is its name itself. Most of the planets in our solar system are named after Roman gods. Uranus, however, breaks this pattern, being named after the Greek god of the sky, Uranos. The Latinized version of this Greek name is what we use today. Had they simply retained the original Greek version, it might have saved a bit of embarrassment for people who sometimes stumble over pronouncing Uranus in a polite way. It even has two commonly accepted pronunciations, Ur-nus and Ur-I-nus, as no one has definitively agreed on the matter. Uranus is also very special in the way it rotates and orbits. It is the seventh planet from the Sun, making it the second to the last of the major planets in our solar system. On average, it orbits at approximately 19.2 astronomical units from the Sun, meaning it is over 19 times further away from the Sun than our own Earth. This distance isn't constant. It varies by 1.8 astronomical units throughout its long year, the biggest difference of any planet. Being so incredibly far from the Sun means it is unimaginably cold, with average temperatures plummeting to -220 degrees Celsius, making it the coldest planet in the entire solar system. Its year, a single orbit around the Sun, lasts an astonishing 84 Earth years. When Uranus was first discovered, astronomers meticulously attempted to predict its orbit. After some time, however, they realized that it wasn't following their predictions precisely. They concluded that the only logical explanation was the gravitational influence of yet another, undiscovered planet. Based on these orbital perturbations, they mathematically predicted where this unseen planet should be. And, remarkably, in 1846, Johann Galle was able to find it, only a degree away from the predicted point. This is how Neptune was discovered. Interestingly, the same theoretical reasoning now surrounds the existence of an yet undiscovered, Planet X, or Planet 9. Some extremely distant objects in our solar system are not orbiting where they should be, and current theory suggests this is because of the gravitational influence of another, still unseen planet. The hunt is now actively on to actually locate this elusive world. What's truly captivating about Uranus is its rotation. Most planets in our solar system spin like a top, upright relative to the plane of the solar system. Not Uranus. No, Uranus has effectively fallen over and is instead rolling along its orbital path. For large portions of its year, one of its poles faces the sun while the other is in complete darkness. You see, its axial tilt is an astounding 97 degrees. This extreme tilt results in incredibly bizarre seasons compared to the rest of the planets. During its solstices, the times of year when the sun is highest or lowest in the sky, one entire hemisphere of the planet is continuously bathed in sunlight, while the opposite hemisphere experiences 42 years of uninterrupted darkness. It genuinely looks as though the planet is rolling along as it orbits. Only a very narrow strip near the planet's equator experiences a semblance of a day and night cycle during this time. But even there, the sun only just manages to rise above the horizon. The poles, on the other hand, endure 42 years of continuous darkness, followed by 42 years of constant daylight. During its equinox, which is the opposite of a solstice, the planet experiences a more normal day-night cycle, with light and dark periods shifting across its surface. Uranus is currently moving away from its equinox, having passed it in 2007, and is now heading back towards a solstice. Uranus rotates once every 17 hours and 14 minutes. However, because its visible surface is not solid, some parts of its atmosphere rotate faster than others. Due to incredibly high winds, certain sections of its atmosphere can complete a full rotation around the planet in only 14 hours. This strange rotation and extreme axial tilt mean that Uranus is the only planet in the solar system that receives more energy from the sun at its poles than at its equator, on average, over its long year. For some unknown reason, though, the equatorial regions are still hotter than the poles, and scientists don't yet have a clear explanation for this discrepancy. Speculation also exists as to why Uranus rotates the way it does in the first place, although the generally accepted theory is that a large Earth-sized planet or protoplanet crashed into Uranus billions of years ago, knocking its rotational axis dramatically onto its side. So, how big is Uranus exactly? It is the least massive of the gas giants, weighing in at about 14.5 Earth masses, compared to Neptune's 17 Earth masses. Its diameter, however, is just slightly larger than Neptune's, measuring approximately 724 kilometers, which is about 4 times the diameter of Earth. Because this mass is spread out over a larger volume, the surface gravity on Uranus is only slightly less than on Earth, at 7.8 meters per second squared, or about 0.89 Gs. That would actually feel quite comfortable for a human. And what is Uranus made of? Scientists believe it has a core, slightly smaller than Earth, composed of rocky silicate material. This core is surrounded by a vast mantle of water, ammonia, and methane ices. Although these materials are referred to as ices, this mantle is in fact very hot, reaching temperatures of almost 5,000 degrees Celsius, and is more like a dense, liquid ocean surrounding the core. So, calling Uranus a gas giant is a bit misleading. It's certainly not gaseous all the way through. The atmosphere itself is relatively insubstantial in comparison, making up only about 0.5 Earth masses of the planet's total mass, with most of Uranus's mass residing in its core and mantle. The atmosphere is primarily comprised of hydrogen and helium, with about 2.3% methane, and then a cloud layer on top. It is this methane in the atmosphere that gives Uranus its distinctive aquamarine or cyan color. Very interestingly, some scientific models suggest that the immense pressure at the base of the mantle on Uranus is sufficient to break apart methane molecules. These carbon atoms from the methane would then compress into diamonds. These diamonds, in theory, would then rain down through the mantle like hailstones. The very base of the mantle could even be a layer of liquid diamond or carbon, with solid diamond bergs floating within it. Let's now move slightly away from the planet to examine its planetary ring system. Uranus, much like the other larger planets in our solar system, does possess rings. It has 13 known rings, which are notably very dark and surprisingly young. Most of these rings are not more than a few kilometers wide, and they are thought to be only about 600 million years old, considerably younger than Uranus itself. They are comprised of extremely small particles, the largest being only a few kilometers across, made of water, ice, and dark, radiation-processed organic compounds. Their albedo, or reflectivity, doesn't exceed 2%, meaning they are darker than wet soil. As we'll see shortly, Uranus has many moons, and its rings are thought to be the result of high impact collisions between some of these moons in the past. It's still unclear why some of the rings maintain such narrow structures. The usual explanation involves shepherd moons, gravitationally hurting the ring particles, but this only accounts for one of Uranus's rings. Uranus's rings were first discovered in 1977 during an occultation of a star. As Uranus moved in front of the distant star, the star's light dimmed several times on either side of the planet, confirming the presence of rings. Uranus has only been visited by a spacecraft once, and that was in 1986 by Voyager 2. Voyager 2 made many discoveries, including most of Uranus's rings and moons, providing us with the first close-up shots of its faint ring system. However, when Voyager flew by, it only brought the total number of known rings to 11. When the Hubble Space Telescope was launched, it also observed Uranus, discovering 2 additional rings that had never been seen before. The outermost of these newly discovered rings is twice as far away from Uranus as the previously thought outermost ring. And as promised, here's a look at Uranus's many moons. Unusually, its moons are often named after characters from English literature. Overall, Uranus has 27 known moons, which are categorized into 3 groups: the 13 inner moons, 5 major moons, and 9 irregular moons. The inner moons are closely associated with Uranus's rings, and some of them may have been the source materials for the rings themselves. The largest of these inner moons is called Puck, at only 162 kilometers in diameter. It is the only inner moon that Voyager 2 was able to capture in significant detail. Interestingly, these inner moons constantly perturb each other gravitationally, making the system very unstable. There's a good chance that some of them may collide again in the future. The 5 biggest moons, in order of their distance from Uranus, starting closest to the planet, are Miranda, Ariel, Umbriel, Titania, and Oberon. Titania is the largest moon of Uranus and the 8th largest moon in the entire solar system, measuring 1,578 kilometers across. As you can see, these are generally very dark objects, with Umbriel being the darkest, except for Miranda, which is primarily composed of water ice. The rest are thought to be a mixture of water ice and rocky materials. These moons may have differentiated interiors, meaning a core of rocky material surrounded by a mantle of ice. Between the core and the mantle, there could very well be a subsurface ocean layer of liquid water. Interestingly, the axial tilt of these large moons is the same as Uranus itself. This means that during a solstice, if you were to stand on one of these moons and look at the sun, it would only ever move in a continuous circle in the sky, never actually setting during the solstice. This means one side of the moon faces the sun constantly, resulting in perpetual daytime. The final 9 known moons are irregular moons. They are likely captured objects, meaning they didn't form with Uranus, but were later gravitationally snared by the planet. They orbit much further out than the last of the big moons, Oberon. They vary in size from 20 kilometers to the largest, Sycorax, which is about 200 kilometers in diameter. Finally, let's explore Uranus's climate and its unusual magnetosphere. The seasons on Uranus are quite unique in the solar system, primarily due to its exceptional axial tilt. Telescope technology has only recently allowed us to resolve detailed features on the surface of Uranus, meaning we've only had a few decades of observations. This makes it difficult to say with certainty if there are consistent changes between Uranian years. However, what has been observed is that as the planet approaches a solstice, its pole brightens significantly and a distinct color forms. Moving away from the solstice, the pole and its color dim. This brightening is thought to be due to the thickening of methane clouds, although the exact cause isn't entirely clear. Seasons also influence the occurrence of storms in the upper atmosphere. Storms are relatively rare on Uranus compared to other gas giants, but they are thought to be caused by these seasonal changes. With ongoing improvements in telescope technology, we've also been able to observe bands stretching around the planet, much like those on other gas planets. However, these bands are mainly visible in infrared light, which is why Voyager 2, observing primarily in visible light, wasn't able to show us them in much detail. In these infrared images, you can also see small storms dotted all over the planet. Another unique characteristic of Uranus is its unusual magnetosphere. Typically, planetary magnetospheres originate from the geometric center of the planet and are roughly aligned with its rotational axis. But that's not the case with Uranus. Its magnetosphere isn't centered on the planet, and it's also not aligned with its rotational axis, being 59 degrees off. This unusual placement means the magnetosphere is much stronger at the North Pole than at the South Pole. One theory for this strange configuration is that the liquid diamond ocean, if it exists, could deflect the magnetosphere. Or, perhaps, the magnetosphere isn't generated in the planet's core at all, but rather within the liquid mantle itself. The magnetosphere is about as strong as Earth's, and because of Uranus's unusual rotation, the magnetotail, the trailing portion of the magnetosphere, corkscrews off for millions of kilometers into space. Now, let's look up into a clear night sky with your naked eye. What planets might you be able to see? Technically, you could observe all of them at one time or another, except for Neptune. It is the smallest of the gas giants and also the furthest major planet from the Sun. It's a truly perplexing place. You might naturally assume that a planet so incredibly far from the Sun would have a relatively placid, unchanging atmosphere devoid of dynamic, ginormous storms and super fast winds, and yet Neptune does. So why is this distant planet as interesting and active as it is? Join me today as we delve into everything you could possibly want to know about Neptune. Let's begin right at the start. Neptune holds a special place in history as the only planet discovered through purely mathematical prediction. You see, when Uranus was discovered, and astronomers were meticulously plotting its orbit, they noticed that Uranus wasn't following their models precisely. From the subtle perturbations in Uranus's orbit, Urbain Le Verrier, in 1846, concluded that there must be another, undiscovered planet exerting a gravitational influence. He mathematically predicted exactly where this planet should be located. And, remarkably, Johann Galle was able to find it only a degree away from the predicted point. Triton, Neptune's largest moon, was discovered just a few days later. However, since then, Neptune has remained poorly understood. Its immense distance from Earth and its very small apparent size meant it couldn't be studied easily from ground-based telescopes. It wasn't until 1989, when the Voyager 2 spacecraft finally arrived, that vast amounts of information about the planet became available. Suddenly, we could see what the planet truly looked like, confirming that it possessed its own planetary rings and revealing a multitude of previously unknown moons. But let's focus on what we know about this distant planet today. Since Pluto's reclassification from a planet, Neptune is now officially the eighth and furthest major planet from the Sun. It orbits at an average distance of 30 astronomical units from the Sun, meaning it's 30 times further than Earth's orbit from the Sun. 30 astronomical units, in other words, translates to a staggering 4.5 billion kilometers. From that, you can understand why it would take a space probe, using current technology, 13 years just to reach Neptune. This incredibly long orbit means it takes a colossal 165 Earth years for Neptune to complete just one orbit around the Sun. This means humanity has only witnessed one full Neptunian year since its initial discovery. This vast distance from the Sun translates to incredibly cold temperatures. The average temperature in Neptune's atmosphere is a frigid -214 degrees Celsius. Its axial tilt is 28 degrees, which is quite similar to Earth's 23 degrees and Mars's 25 degrees. This similarity in tilt means that Neptune experiences seasons much like Earth and Mars do, with the significant difference being that each of these 4 seasons lasts a monumental 40 Earth years. At this very moment, Neptune's southern hemisphere is experiencing spring. During this spring, the southern hemisphere receives slightly more sunlight and appears noticeably brighter. This increase in brightness is actually quite remarkable, which is strange when you consider that the Sun is 900 times dimmer on Neptune than on Earth. Despite this vast distance, even a small increase in sunlight makes a noticeable impact. The increased sunlight levels in the southern hemisphere subtly warm it up by about 10 degrees Celsius compared to the rest of the planet. This comparably higher temperature releases frozen methane into the stratosphere, causing its increased brightness, whereas elsewhere on the planet, methane remains frozen and stays deeper in the troposphere. Just a quick recap of the atmospheric layers of a planet. The troposphere is the lowest atmospheric level, where most weather occurs, followed by the stratosphere above it. Above those layers are the mesosphere, the thermosphere, and then the exosphere, the very outermost layer. But that's a very interesting topic in itself, and we'll save it for another video. If you look at the weather on Neptune, it actually boasts the fastest wind speeds of any planet in our solar system. Wind speeds blowing westward on the equator can reach a staggering 2,160 kilometers per hour, nearly a supersonic flow. And, interestingly, most of Neptune's winds travel retrograde, or opposite, to the planet's overall rotation. Distinct bands are also formed on the planet, much like Jupiter and Saturn, as well as colossal storms. When Voyager 2 passed by the planet in 1989, it observed the Great Dark Spot, a storm about the size of Earth, churning through its atmosphere. Voyager also spotted a smaller storm known as the Small Dark Spot, located south of its larger sibling. As Voyager 2 approached Neptune, this smaller storm actually changed in shade from dark to light. When the Hubble Space Telescope was launched, astronomers were curious to see the fate of these storms, to determine if they were permanent features like Jupiter's Great Red Spot. But when Hubble was pointed at Neptune in 1994, these storms had completely vanished. Since then, storms have appeared and disappeared on Neptune, giant bright, high-altitude clouds also coming and going. But why then doesn't Uranus, which is very similar in composition and size to Neptune, also have such a blustery, active atmosphere? Don't get me wrong, wind speeds on Uranus are fast too, but they don't compete with Neptune's, reaching only 900 kilometers per hour. Can all this difference only be due to interactions with the Sun and its seasons? Something else must be at play here to explain the extreme weather conditions on Neptune. The answer may lie deep beneath Neptune's surface. I mentioned that Neptune is the furthest planet from the Sun, so you would naturally assume it's also the coldest. But surprisingly, Uranus is actually the coldest planet in our solar system. This is because Neptune radiates a significant amount of heat from within, whereas Uranus radiates hardly any excess internal heat at all. This difference could be explained by a theory that a large, Earth-sized body crashed into Uranus billions of years ago, which depleted all of its primordial internal heat, leaving it much colder. Astronomers now theorize that the more active weather on Neptune might be due, in part, to this higher internal heat driving atmospheric convection. So, what is Neptune actually made of? Its internal structure and atmosphere are thought to be very similar to Uranus. Its atmosphere is primarily composed of about 80% hydrogen and 19% helium, with very small amounts of methane. It's this methane, however, that gives Neptune its beautiful blue color, although it's a darker shade of blue compared to Uranus's cyan. Again, like Uranus, there is believed to be a liquid mantle of water, ammonia, and methane ices surrounding a core. And where the core and the mantle meet, the pressure is so immense that the methane may break apart and diamonds could form under the pressure. It's likely not diamonds as you or I know them, but there could be a liquid carbon ocean with solid diamond bergs floating in it, and diamonds raining down through the mantle like hailstones. This is still just a theory, though, as technology has only recently started to be able to recreate such extreme pressures in laboratories. Around the core of Neptune, the pressure is thought to be 7 million bar, or 700 gigapascals, which is about 7 million times the pressure of Earth's atmosphere at the surface. Even the magnetospheres of the two ice giants share similarities. Neptune's magnetic field is offset 47 degrees relative to its rotational axis. When Voyager 2 discovered this unusual tilt about Uranus, the initial theory was that it had something to do with Uranus's extremely unusual axial tilt. But then, Voyager 2 found the exact same thing about Neptune, which has a much more normal axial tilt. So, the current theory is that the magnetic field is either not generated in the core, but rather by an electrically conducting liquid mantle, or that the mantle itself deflects the magnetic field originating from the core, which gives it this weird offset in relation to its rotational axis. Every planet in the solar system actually has a magnetic field that isn't perfectly aligned. Even Earth's magnetic north is slightly different from its geographic North Pole, but it's only Uranus and Neptune that have such an extremely tilted and off-center magnetosphere. Auroras do exist on Neptune too, but they are different from what you might expect, as they are extremely faint. This is due to particles not getting as charged from the Sun at such a great distance. And because of the peculiar direction of Neptune's magnetosphere, they are mainly Type B auroras or SR arcs. Earth also experiences these, but they are not visible to the naked eye, and you need sensitive scientific instruments to even detect their presence. They could be stretching across the entire sky without you even knowing about them. Another difference with Neptune's SAR arcs is that they are not only found around the poles, but are also observed around the mid-latitudes of the planet. Zooming out a bit from Neptune, we come to its ring system. Like all other gas giants, Neptune does have a ring system, although it is extremely faint, as it is not very dense and is exceptionally dark in color. Having these rings against the black backdrop of space, and also being so incredibly far away from the Sun, makes them very difficult to see. But there are 5 known rings in total, and they are named after people involved in the discovery and research of Neptune. The innermost is the Gal ring, which is very faint and quite wide, spanning 2,000 kilometers. Next is the first bright ring, Leverrier. Although it's considered bright for Neptune, it's only 113 kilometers wide. Next, and connected to it, is the Lassell ring, a very faint band 4,000 kilometers across. On the edge of this ring is the Arago ring, which is slightly brighter than the Lassell ring and less than 100 kilometers wide. Lastly, there's the outermost and most thoroughly researched ring, the Adams ring. It's only 30, 5 kilometers wide, but is one of the brighter rings. It's particularly interesting because it's slightly inclined and contains distinct, bright arcs within it. These arcs have been remarkably stable since their discovery in 1980. Usually, planetary rings are uniform throughout, so these arcs must be material clamping and clustering together within the ring, but the precise reason for this phenomenon is currently unknown. Lastly, I want to talk about Neptune's moons. Neptune has 14 known moons, which are named after various water deities in Greek mythology. The most famous, and by far the largest, is the moon Triton, which actually contains most of the mass of all of Neptune's moons put together. I personally think it is one of the prettiest moons in our solar system, with its amazing patterns and a beautiful burnt orange color. What is most interesting about Triton is the fact that it orbits in retrograde, meaning it orbits in the opposite direction to Neptune's rotation, and also at a significant inclination to Neptune's equatorial plane. This strongly implies that it is probably a captured object, and not something that formed alongside the planet. Triton itself might even be the ultimate cause of Neptune's rings, as its immense gravitational influence could have disrupted the orbits of other moons in the past, possibly causing them to collide and break up into what is now the rubble of the rings. Triton is even larger than Pluto, and also possesses a tenuous atmosphere. Voyager 2 even observed faint clouds on its flyby of the moon. The next biggest moon is Proteus, which has a slightly irregular shape. Normally, we only see this kind of irregular shape on much smaller objects, like asteroids. But Proteus is actually quite large, at 400 kilometers across, even bigger than Saturn's spherical moon Mimas. Why it isn't a perfect sphere is explained by past collisions of objects hitting the moon, leaving behind massive craters that have significantly altered its shape. The inner irregular moons orbit relatively close to the rings, with some even acting as shepherd moons, helping to maintain the ring structure. The outer irregular moons are all likely captured moons. Some of these irregular moons orbit prograde, in the same direction as Neptune's rotation, while others orbit retrograde, in the opposite direction. The outermost known moons of Neptune are Naso and Samoth, and they are the furthest out satellites of any planet that we know of to date. They take a massive 25 years to complete just one orbit around Neptune. This is because Neptune has a very large Hill sphere, which is the region in space where the planet's gravity overcomes the Sun's gravity. It possesses such a large Hill sphere because it's already so incredibly far from the Sun, meaning the Sun's gravitational influence is significantly weaker in Neptune's vicinity compared to, say, at Jupiter's location. Well, thank you for watching. Did you learn something interesting about Neptune today? What mysteries would you like to see solved? We're still working our way through remastering the planets in our solar system series. What planet would you like to see us do next? Let us know in the comments below, and I'll see you next time. Thanks for watching, and thanks to our dedicated crew of astronauts over at Patreon, who help us make scientific knowledge freely available to everyone. Chasing the algorithm can be a bit hit and miss sometimes, so your contributions truly help us keep making the content we love. And if you want to join the Patreon, there's never been a better time to get in on the party. Just sign up with the link in the description. When you join, you'll be able to watch the whole video ad-free, see your name proudly displayed in the credits, and submit questions directly to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time. The gas giant planets, those colossal worlds of swirling hydrogen and helium, hold a special place in our solar system. They are the behemoths, the guardians, the distant, enigmatic worlds that shape much of what lies within their gravitational grasp. We've explored Saturn, Jupiter, Uranus, and Neptune. But there's so much more to grasp about these incredible entities. Let's step back and consider them as a group, understanding what they didn't teach you in school about their collective nature, their formation, and their profound influence on our cosmic neighborhood. Think about the sheer scale for a moment. Jupiter alone is more than twice as massive as all the other planets combined. Saturn, while less dense, is still a titanic presence. Uranus and Neptune, the ice giants, are still many times the size and mass of Earth. These aren't just bigger versions of rocky planets, they are fundamentally different. Their formation, for instance, is a tale of cosmic dust and gas coalescing in the early, chaotic solar system. Unlike the terrestrial planets, which formed from rocky planetesimals colliding and sticking together, the gas giants likely started with solid, icy cores that quickly grew massive enough to gravitationally attract vast envelopes of hydrogen and helium gas from the surrounding protoplanetary disk. This process is known as core accretion. Imagine tiny dust grains, then pebbles, then small boulders, all made of ice and rock, slowly bumping and clumping together in the colder, outer regions of the solar nebula. As these icy cores grew, reaching maybe 10 to 15 times the mass of Earth, their gravity became incredibly powerful. At this critical point, they started rapidly pulling in the abundant hydrogen and helium gas that made up the bulk of the solar system's initial cloud. This runaway accretion is what allowed them to swell into the colossal worlds we see today. The speed at which this happened is crucial. If they didn't grow fast enough to grab the gas before the sun's intense radiation blew it all away, they wouldn't have become gas giants. The presence of these gas giants, particularly Jupiter, also played a crucial role in shaping the rest of the solar system. For example, Jupiter's immense gravity is thought to have prevented a fifth rocky planet from forming in the region between Mars and Jupiter. Instead, its gravitational stirrings repeatedly disrupted the orbits of nascent planetesimals there, leading to collisions that pulverized them rather than allowing them to accrete into a larger body. This is why we have the asteroid belt, a fascinating graveyard of planetary building blocks, rather than another terrestrial planet. Furthermore, these gas giants, especially Jupiter and Saturn, are often credited with protecting the inner solar system from a bombardment of comets and asteroids. Their massive gravitational fields act like cosmic bouncers, either flinging dangerous incoming objects out of the solar system entirely or capturing them in stable, safe orbits. Without this protective shield, Earth might have experienced many more devastating impacts throughout its history, potentially making the emergence of complex life much less likely. So, in a very real sense, we owe a debt of gratitude to these distant, swirling behemoths. Let's delve deeper into their internal structures. While we often call Jupiter and Saturn gas giants, and Uranus and Neptune ice giants, these terms can be a bit misleading if you imagine them as purely gaseous. Deeper within their atmospheres, the pressure and temperature become so extreme that the familiar states of matter simply cease to apply. For Jupiter and Saturn, as we discussed, hydrogen transitions from a gas to a liquid, and then, under truly immense pressures, to a liquid metallic state. This liquid metallic hydrogen is a fantastic conductor of electricity and is responsible for generating their powerful magnetic fields through the dynamo effect. Uranus and Neptune, on the other hand, are dominated by what scientists call ices. But again, these aren't the frozen blocks of ice you'd find in your freezer. At the pressures and temperatures within their mantles, water, ammonia, and methane exist in a supercritical fluid state, acting more like a hot, dense, electrically conductive ocean. This is why they are referred to as ice giants. The primary building blocks beyond their hydrogen and helium envelopes are these volatile compounds, not primarily rock. The precise composition and phase of matter in these deep interiors are still subjects of intense research, with ongoing debates about whether diamond rain or liquid carbon oceans exist. Their atmospheres are also marvels of dynamic weather systems. Jupiter's Great Red Spot is the most famous example, a storm that has raged for centuries, but all the gas giants exhibit incredible atmospheric phenomena. Powerful jet streams, driven by internal heat and rapid rotation, create those distinct banding patterns. These winds can reach supersonic speeds, far exceeding anything ever recorded on Earth. The colors, as we learned with Jupiter and Saturn, come from trace amounts of compounds that are chemically altered by sunlight or by interactions with deeper atmospheric layers. On Uranus and Neptune, the methane in their atmospheres is particularly crucial, absorbing red light and scattering blue light, giving them their characteristic blue and cyan hues. The rings of these planets also offer a window into their past and present. Saturn's rings are undeniably the most spectacular, but all four gas giants possess them. These aren't solid structures, but rather countless particles, ranging from microscopic dust grains to boulders the size of houses, all orbiting the planet. The origin of these rings is still debated, but theories suggest they could be the remnants of shattered moons that came too close and were ripped apart by the planet's powerful tidal forces, or perhaps leftover material from the early solar system that never fully accreted into a larger body. The gravitational interactions with small, shepherd moons play a vital role in maintaining the narrow, distinct structures of many rings, preventing them from spreading out or dissipating entirely. The dynamics of these ring systems are incredibly complex, constantly evolving under the influence of gravity, collisions, and subtle planetary perturbations. Magnetic fields are another unifying feature of the gas giants, though each is unique. We've talked about Jupiter's immense magnetosphere, the most powerful of any planet, and Saturn's strangely aligned field. Uranus and Neptune, with their off-center and tilted magnetic fields, present their own puzzles. These magnetic fields are not just academic curiosities. They are crucial for understanding the internal dynamics of these planets and for shaping their environments. They trap charged particles, forming intense radiation belts, which can be hazardous to spacecraft but also create magnificent auroras at the poles. The interaction of these magnetospheres with the solar wind, and in some cases, with their own moons, is a complex interplay of cosmic forces. The moons of the gas giants are, in themselves, entire worlds waiting to be explored. From Jupiter's Galilean moons, each a unique realm of volcanic activity, subsurface oceans, or ancient cratered landscapes, to Saturn's Titan, with its thick atmosphere and methane lakes, and Enceladus, with its erupting water plumes hinting at habitability. Uranus and Neptune also boast their own retinues of diverse satellites, many of which are likely captured asteroids or comets. These moons are not just passive companions, they are active participants in their planetary systems, often tidally heated, geologically active, and sometimes, surprisingly, potential abodes for life. The study of these moons has become a major focus of planetary science, pushing the boundaries of what we consider habitable zones. One of the most profound aspects of studying the gas giants is what they tell us about planetary formation and evolution, not just in our own solar system, but across the universe. As we discover exoplanets, planets orbiting other stars, we find that gas giants are incredibly common. Many of these exoplanets are hot Jupiters, giant planets orbiting extremely close to their stars, a stark contrast to our own solar system's arrangement. Understanding our own gas giants helps us interpret these distant worlds, providing a baseline for comparative planetology. It allows us to test our models of how planets form, migrate, and interact within a stellar system. The Grand Tack hypothesis, for example, is one such model that attempts to explain the current architecture of our solar system with Jupiter playing a starring role. This theory suggests that early in the solar system's history, Jupiter actually migrated inward towards the Sun, perhaps as far as where Mars is now, before being tacked back outwards by the gravitational influence of Saturn. This migration would have had a dramatic impact, scattering planetesimals, clearing out the inner solar system, and potentially explaining the relatively small size of Mars. It's a testament to the dynamic nature of early planetary systems and the immense power of these gas giants. The ongoing exploration of these planets continues to challenge our assumptions. Every mission, every new dataset, seems to reveal more questions than answers, pushing the boundaries of our scientific understanding. The mysteries of their deep interiors, the precise mechanisms of their magnetic fields, the drivers of their extreme weather, and the origins of their rings are still active areas of research. These aren't static, unchanging worlds. They are dynamic, evolving systems full of unexpected phenomena. Consider the role of internal heat. We discussed how Neptune radiates more internal heat than Uranus, contributing to its more active atmosphere. This internal heat comes from a combination of primordial heat left over from their formation and, for the larger ones, ongoing gravitational contraction. This is a subtle but constant process where the planet slowly shrinks, converting gravitational potential energy into heat. This internal energy can be a crucial factor in driving atmospheric circulation, creating powerful convection currents that churn the deep layers of gas and fluid, ultimately leading to the visible storms and patterns we observe. The interaction between these planets and their vast families of moons is another complex dance. Tidal forces, the differential gravitational pull exerted by the planet on its moons, can generate immense heat within the moons themselves. We see this vividly with Jupiter's moon Io, the most volcanically active body in the solar system, constantly churned by Jupiter's powerful tides. Even on more distant moons like Europa and Enceladus, tidal heating is thought to maintain subsurface liquid water oceans, making them prime targets in the search for extraterrestrial life. This constant gravitational tug of war is a fundamental process shaping the geology and potential habitability of countless worlds in the outer solar system. The study of the gas giants also involves understanding their magnetospheres in even greater detail. Beyond just creating auroras, these vast magnetic bubbles protect the planets and their inner moons from the harsh solar wind. But they also trap charged particles, forming intense radiation belts that can strip away the atmospheres of moons or even sterilize their surfaces. The balance between protection and hazard is a delicate one, and each planet's magnetosphere creates a unique environment for its orbiting companions. The complex, dynamic behavior of these magnetospheres, influenced by both internal planetary dynamos and external solar wind interactions, remains a frontier of scientific exploration. Furthermore, the very composition of these gas giants offers clues about the initial conditions of the solar nebula from which our entire system formed. By measuring the precise ratios of elements like hydrogen, helium, methane, and ammonia, scientists can deduce the temperature and density gradients in the early solar system. Deviations from expected cosmic abundances can indicate processes like planetary migration, where a planet's formation in one region and subsequent movement to another alters its chemical signature. This kind of chemical fingerprinting is a powerful tool for unraveling the grand narrative of our solar system's birth and evolution. The sheer remoteness of Uranus and Neptune, the ice giants, means that our understanding of them is still relatively nascent compared to Jupiter and Saturn, which have seen multiple dedicated orbiter missions. The data from Voyager 2, a flyby mission from decades ago, still forms the bedrock of much of what we know about them. This highlights the urgent need for future missions to these distant worlds such as NASA's proposed Uranus orbiter and probe, which would provide an unprecedented opportunity to study these mysterious planets up close, potentially revolutionizing our understanding of them, just as Cassini did for Saturn. Such missions are incredibly challenging and expensive, requiring decades of planning and technological innovation. But the scientific payoff is immense. Imagine an orbiter spending years circling Uranus, unraveling the mystery of its tilted magnetic field, observing its bizarre seasonal changes in detail, and sending back high-resolution images of its elusive rings and moons. Or a probe plunging into Neptune's atmosphere, directly sampling its supersonic winds and tracing the origins of its internal heat. These future endeavors promise to unlock even more of the universe's secrets, pushing the boundaries of human knowledge and our place within the cosmos. The gas giants are not just distant lights in the sky. They are active, dynamic worlds, each with its own personality and its own set of profound questions. They remind us of the incredible diversity of planetary systems and the endless wonders that await discovery. From the swirling storms of Jupiter to the elegant rings of Saturn, the tilted mystery of Uranus, and the blustery blue of Neptune, these giants are a testament to the raw power and beauty of nature on a cosmic scale. Understanding them is key to understanding the story of our solar system, its past, its present, and its potential future. They are also a constant reminder of the incredible ingenuity and perseverance of humanity to send robotic emissaries billions of kilometers into the cold, dark reaches of space, to gather data, and to transmit it back across vast distances is an astonishing achievement. Each image, each data point, represents countless hours of scientific inquiry, engineering brilliance, and daring exploration. And the story is far from over. The clues that Cassini Voyager, Juno, and other missions have provided are just the beginning. The gas giants continue to beckon, promising even more profound revelations for future generations of explorers and scientists. The very concept of a gas giant challenges our Earth-centric view of what a planet can. We have journeyed through the astounding complexities of Saturn, Jupiter, Uranus, and Neptune, each a magnificent and mysterious world in its own right. We started with the incredible Cassini-Huygens mission, a testament to human ingenuity that completely revolutionized our understanding of Saturn and its intricate system of rings and moons. Cassini's 13 years in orbit provided a staggering amount of data, unveiling the true nature of its shepherd moons, the dynamic propeller features within its rings, and the breathtaking beauty of its polar hexagon. It showed us the active icy plumes of Enceladus, hinting at a subsurface ocean and potential for life, and provided an unprecedented view of Titan's Earth-like atmosphere and liquid methane lakes. Even in its final, fiery descent, Cassini was collecting invaluable data, a fitting end to a mission that expanded our scientific horizons. Then, we turned our gaze to Jupiter, the undisputed king of our solar system, a planet so massive it affects the Sun itself. We explored its colossal storms, like the iconic Great Red Spot, and delved into its internal structure, where hydrogen transforms into a metallic liquid under immense pressure. We learned about its powerful magnetosphere, a shield that protects its inner moons from solar winds, but also creates a deadly radiation environment. Jupiter's immense gravity acts as a cosmic vacuum cleaner, protecting the inner planets from potentially devastating asteroid and comet impacts. It's a true protector, a vital asset to our solar system. Our exploration continued with Uranus, the peculiar ice giant that rolls on its side. Its extreme axial tilt creates seasons unlike any other planet, with decades of continuous daylight or darkness at its poles. We discussed its dark, faint rings, which are thought to be surprisingly young, and its numerous moons, many named after characters from English literature. Uranus's unusual, off-center magnetosphere remains a puzzle, challenging our understanding of how planetary magnetic fields are generated. The methane in its atmosphere gives it that distinctive blue-green hue. Finally, we reached Neptune, the furthest and coldest of the major planets, yet surprisingly active with the fastest winds in the solar system. Discovered through mathematical prediction, Neptune's deep blue color, also from methane, hides a dynamic atmosphere with storms that appear and vanish. Its internal heat drives powerful weather systems, a stark contrast to its icy counterpart, Uranus. Like Uranus, Neptune also has a highly tilted and offset magnetic field, adding to the mysteries of ice giants. Its faint ring system and diverse collection of moons, including the enigmatic, retrograde, orbiting Triton, further highlight the unique characteristics of this distant world. The gas giants are not merely distant, beautiful objects. They are crucial components of our solar system, influencing everything from the orbits of other planets to the potential for life. Their study helps us understand not only our own planetary neighborhood, but also countless exoplanets, many of which are gas giants themselves. The data collected by missions like Cassini will continue to be analyzed for decades, yielding new discoveries and deepening our scientific knowledge. Future missions, such as NASA's Dragonfly to Titan and others planned for Jupiter's icy moons, promise to unravel even more secrets. As we conclude this deep dive into the gas giant planets, I hope you've found this journey through their incredible facts and mysteries as fascinating as I have. The universe is a vast, wondrous place, full of things still to be learned and questions still to be answered. Thank you for joining me on this exploration. Stay curious, keep looking up, and I'll see you next time as we continue to explore the incredible universe around us. Good night. The gas giants, sometimes collectively known as Jovian planets, are truly distinct from the terrestrial worlds like Earth and Mars. They are primarily composed of hydrogen and helium, with deep atmospheres and likely dense, rocky cores, though without a clearly defined solid surface. Jupiter and Saturn are considered the true gas giants due to their composition, while Uranus and Neptune, with their larger proportions of heavier volatile substances like water, ammonia, and methane ices, are often classified separately as ice giants. The study of these colossal worlds has become even more vital with the discovery of thousands of exoplanets beyond our solar system. Many of these distant worlds are also gas giants, and understanding our own Jovian planets helps us unravel how other planetary systems form and evolve. They play a profound role in shaping their entire planetary systems, with their immense gravity stabilizing or perturbing the orbits of other planets. Jupiter, for instance, acts as a gravitational shield, deflecting or absorbing comets and asteroids that might otherwise pose a threat to the inner planets. The moons orbiting these giants, like Europa, Ganymede, Callisto, Titan, and Enceladus, are particularly intriguing, with their subsurface oceans or thick atmospheres, making them potential candidates for harboring life. Future missions are already planned to continue this incredible journey of discovery. NASA's Juno spacecraft, which arrived at Jupiter in 2016, has had its mission extended through 2025, allowing for close flybys of Jupiter's major moons, Ganymede, Europa, and Io, providing even more data on their unique characteristics and Jupiter's powerful auroras. The Europa Clipper mission is expected to explore Europa, studying its ice shell, ocean, and geology in detail. And as we discussed, NASA's Dragonfly is slated to launch in 2028, a rotorcraft lander specifically designed to explore the fascinating surface of Titan. China also has plans for a Jupiter and Callisto orbiter with a Uranus flyby, launching in September 2029. These ongoing and upcoming missions promise to deepen our understanding of these distant worlds, addressing many of the mysteries that still perplex scientists. Planetary science itself is a multidisciplinary field, integrating aspects of astronomy, physics, geology, and meteorology, offering a comprehensive framework for exploring the natural sciences. It's a field that inspires curiosity and wonder, not just in professional scientists, but in everyone who are interested in it,